Okay, so let's go right into the presentation. Writing custom eBPF programs for observability purposes. What exactly is eBPF? The extended Berkeley packet filter is an evolution of the original BPF technology. It extends the capabilities of BPF by providing a more powerful and flexible way to perform more features like dynamic tracing, network analysis, performance monitoring. But mainly, how it does this is by providing a framework for you to write kernel compatible sandbox programs that can be executed directly in your kernel space without modifying the kernel code itself or without running afoul of any security protocols. You get a flexible tool that you can use to program observability, control, or enhance your kernel behavior. So looking here, we see the architecture, basically the process by which the eBPF program is created and is loaded to the kernel space. So basically you start with the C source or like a C program, eBPF program, and then this program is converted to bytecode before being converted to bytecode by the compiler before being attached into the or loaded into the kernel space and attached to either hooks or events or system calls as the case may be. So between the compiler and the loader stage, verifier goes through your programs to ensure that okay, there are no loops, there are no out of memory or any security protocols, and then this makes it a kernel compatible program that can be executed as machine code within the kernel space. Why is eBPF a game changer for observability? It's because you get that flexibility, you get that ability to basically execute code within your kernel space. This gives you kernel level visibility, something that you can use to like be able to get custom metrics way before any user space application might see it. You get them like almost immediately in runtime as the operations are being executed. You get that visibility. You get there's no code instrumentation need, no manual instrumentation is needed for you to get this visibility because yeah, eBPF is a kernel compatible tool or technology. Basically, it works for most or any kernel version, and you do not need to basically create or mess with the security of your kernel. Also, low overhead. As we said earlier, everything gets compiled or extended to machine code, and all your scripts, however flexible, gets compiled into the machine code that is executed at runtime at the same time as your operations, basically. Real world use cases. So a lot of companies have used this tool. A lot of companies have extended this to using it as a foundation for tracing system calls, network visibility, performance profiling, security monitoring. And I linked in some examples from Netflix, Apple, basically what they have done with this tool. We have a demo with I added in a GitHub link. So if that is useful to us, but let's see. So this is the GitHub link where the code instructions on how to basically set your environment to test the eBPF code as well. Usually, or like for this particular one, you just need an Ubuntu instance. I'm going to be using AWS instance, free tier micro, or yeah, the And that's all I need to just test these two demos. First, the packet logger, which would basically get traffic packets and log it in to a BPF map. So let's just see how that works. I have already done this. I already put up the environment basically. So we can just test this, just basically sending in packets, sending in traffic packets, and then we'll see that this has been, a BPF map has been generated for us in packet counters and packet events, and we can be able to see this particular one. This BPF map is accessible to kernel space, but also accessible to the user space as well. It can be exported, it can be pushed towards your observability tools like Prometheus and Grafana, basically, with user space tools. But then for this particular demo, we used a C program to basically pass the packet information from our traffic, log that data into basic BPF map, and with a counter also to count, to basically generate metrics, just custom metrics like a counter, get the packet size, also put that in there as well. So once you do this, once you like put down your logic, your eBPF logic, you then load it. Like I said earlier, you compile it. This is the compiling stage. You compiled it, loaded it into this interface, and then, yeah, you could immediately see that it has been loaded. This is the packet observer. And then we have tested it and seen that, okay, the map has been created and been stored in the kernel space where it can be accessed by user space programs. But then that is not the only way to create or to utilize your eBPF programs. You can create native C eBPF programs, but there are also extensions such as Python extensions, Go, Rust in BCC, Cilium library, and then Aya. These extensions offer like abstractions of the base code. They help you basically do more with your eBPF programs, make it easier for you. However, they also have their performance cost basically because you get more delayed execution and a larger footprint. We'll see this with our next demo where we use the BCC tool to create an eBPF program in Python. So this is the Python code. You can see that BCC is imported and then used in passing your main BPF programming and logic, and then that is now used to initialize and process events within the code instructions. So this particular code traces, first we'll pull up an Nginx web service, and then we'll add some files into it. And then you can trace the access, you can trace user access to those files, basically just logging or accessing the files and generating metrics from that. I have done all this, installing, testing, creating the HTML files that we would then trace. I've done all this in the Ubuntu instance. So we just start that up and then try and test it. Let's go with the load test instead. So the load test of our Nginx web service in another terminal, and then it basically makes like 100 requests to all different pages, and then we can see it here. The operations, this is our BPF program basically reacting and basically carrying out our program logic for the 100 requests that web service receives. The program logic is up to you. You can, whatever you want to do with that information, whatever you want to do with the visibility or the access to the visibility that you have, whether you want to create custom metrics from that, whether you want to export the data directly to your observability tools, your analysis tools, whether you just want that information logged, eBPF gives you the access and gives you the ability to program your custom logic into the kernel space. So we have seen two demos now, one using native C programming to create eBPF program and attach that to the kernel space, another using Python basically. And then as we saw, we didn't need to load or to attach manually. The Python BCC program did that at runtime for the Python execution. Yeah, so extending eBPF. Like I said earlier, you have either those custom metrics or you have the BPPF, the BP, BPF map, basically with your data, and you can export this. You can utilize it with a user space application however you need. For extending eBPF, there's a wide range of tools. OpenTelemetry has one, Meteors has one, Grafana has one. Basically, all this based on eBPF and utilizing this revolutionary technology that gives you access to kernel space for your observability tools, your observability tooling. So here we see a kind of ecosystem map, basically looking at all the projects, XDKs that are available to you for whatever use case you have. For observability and monitoring, we have Pixie. Give me a moment. We have Pixie, which is a Kubernetes observability tool that basically takes away the need for manual instrumentation as it is based on eBPF. You have Parker, which gives you continuous system profiling, Periscope, another continuous profiling platform. Deepflow has automated observability with tracing. And you have network tools like Cilium, hopefully which gives you like that networking for your Kubernetes purposes. There are also program management tools. You have Leaf, BPF Man, and Bumblebee. Basically, this ecosystem, your eBPF ecosystem, has a wide range of variety of tooling, variety of management and optimization tools that you can use to better utilize and optimize observability, networking, or security across your infrastructure. Here I linked in some more learning docs basically to see more on how eBPF came to be, on the infrastructure of eBPF, on basically learning how to utilize eBPF more, and then an article eBPF for FANG, which basically goes through how startups or how companies, tech giants like Apple and Netflix are using eBPF for their tools. This is the end of my presentation. The GitHub links, slides as well will be made available to you. So thank you very much for taking the time to go through to this presentation.